Okay, so if you're going to do dynamics, right? Dynamics just means that we're going to use like F equals ma. Okay, if you're going to do dynamics with rotation, with rolling, okay, we've got to come up with the force needed, the tangential force needed at the edge, right? If we exert a force like this, right, okay, on this thing to cause it to angularly accelerate, okay. So what I'm going to do is I'm just going to pull out some formulas here. We know that torque is I alpha. We also know that torque is whatever that force is you're exerting times whatever this radius is, right? Okay, so whatever that is, whatever that radius is, it's just R times F, right? Well, if torque is I alpha and torque is RF, then it must be true that RF is I alpha. And then if we want the force needed to accelerate it, right, force is just I alpha over R. Okay, that's the force needed at the edge to accelerate. This isn't that's without friction and everything. These are hard enough without friction, so let's just go with that, right? Okay, so this will be the force needed to accelerate something, right? Angularly, okay? Look how fast you're learning, look at that. Okay, now if we're going to solve for the acceleration of this thing down the plane, what we've got to do is we've got to go, okay, there's a force acting down this plane. That's going to be our what we learned in inclined planes, right? So mg sine theta, right? Okay. Now that's sort of tricky, right? You got the sine of that thing. We know that this length is 2.9 meters, right? And then we also know that this height of this plane is 0.34 meters, right? I'm just looking at the problem here, right? 0.34. So isn't the sine of that angle, isn't the sine just, the sine of theta, isn't that just 0.34 divided by 2.9? Seems like it's cheating, but it is, right? This is the opposite side, right? This is the hypotenuse, right? So we actually never have to touch our calculator and use the sine function for this, right? Anyway, there's this mg sine theta that's down the plane, right? And so what we do is we go, okay, mg sine theta is equal to ma, that's the force needed to accelerate it linearly, right? And then it's plus I alpha over r. That's the force. So this is to cause translational acceleration. This causes rotational acceleration. Okay? And so the mg sine theta is going to provide the force needed to do that. Okay? So now let's go. We'll do the standard substitutions. And the standard substitutions are that the moment of inertia is going to be, well, it's a cylinder, right? So we're going to substitute for the moment of inertia, and we're going to substitute for the angular acceleration, right? Angular acceleration is just linear acceleration over r, right? And in this case, our angular, or our moment of inertia is 1/2 mr squared, okay? I'm going to substitute that, right? So that's what we have now. We go mg sine theta is equal to ma plus, and then I'm going to substitute, right? I'm going to go 1/2 mr squared, and then the alpha is a over r, and then all of that is above r, okay? Again, the radius is going to cancel, watch. This guy cancels one, that guy cancels the other one, right? And we end up with ma plus 1/2 ma. Well, that's 3/2 ma. Okay, so again, you got to remember this. Start off with this, right? If you can remember this, I guess that's a little bit, I think, contrite. I think this is a little harder, but so mg sine theta, the parallel force, right, from our inclined planes becomes ma, regular old translational acceleration and rotational acceleration. Okay, the force needed to do both. Okay, and then you substitute the moment of inertia and you substitute for alpha, and you end up with that, right? So now we've got mg sine theta is 3/2 ma. Obviously the mass cancels, right? And we can solve for a. A is 2/3 g sine theta. Okay, I will want you to be able to make these substitutions and come up with a as, something times g sine theta, right? Okay, I want you to be able to do that step by step. Show me all the steps. Okay, now we're set though. Now we can plug numbers in. So let's do that. A is 2/3, g is 9.81, right? And then sine of theta, remember sine is opposite over hypotenuse. This comes from SOHCAHTOA. Again, this is sort of tricky, I think, right? So 0.34 over 2.9, right? Over 2.9. And now we can get a number without even using the sine. Now, by the way, if you don't understand that, go ahead and find the angle with the inverse sine of 0.34 over 2.9, then take the sine of that angle. That's like a math joke. I'm hoping you're laughing. Are you laughing? Nobody laughed at that in class. I thought it was funny. Times 0.34 divided by 2.9. And I'm getting that the acceleration is 0.76675 meters per second squared, right? Now, dynamics will get you the acceleration, and then obviously with acceleration we can find the final velocity, right? So let's do that here. The last step is I might need all that space, right? Suvat for v, right? So v squared is u squared plus 2as. It's always this formula, right? Because we know the length of the plane, right? So v squared is 0 squared plus 2 times this guy, right? 0.76675. And then how long is our plane? 2.9. All right. So I'm going to go square root of 2 times the answer I just got times 2.9. I get 2.1088. Ta-da. So again, with this method, you start off with parallel force provides the force to linearly accelerate and rotationally accelerate, right? Okay. You substitute for the moment of inertia. You substitute for the angular velocity. Again, to make this a linear, all linear, right? We always solve in linear land. Although some of them you can solve in rotational land, right? Then you cancel the r's, you combine the terms, you cancel the mass, you solve for a, and then you plug in. Now the trick is the angle. I never give you the angle, so what you have to do is you have to make an expression for the sine of it, right? You'll always know the height and the length, right? And if you didn't know that, right, if you knew something else, like the length of this and the length of that, you could use the Pythagorean theorem. But I'm not going to make it that hard because this is hard enough.